I'm Ikra. I'm a PhD researcher in University of Nottingham and also in ESR of Egypt.
Hello everyone, my name is Angel Peña. I am also a PhD student at University of Nottingham. My project is Utopia.
Hello, my name is Arun Khilnani, and you guessed it, I'm also a PhD student at the University of Nottingham, and I'm also part of Utopia project.
And today we are here to give you a hardware demonstration of electromagnetic compatibility phenomena of crosstalk through a cable bundle model. So I told you about the cable bundle model, but before diving into the details, I think it's important that we see what equipment we are using in this setup. So the first equipment that we have is the EMI receiver. It is connected with the victim cable that I will explain later. Then we have the power supply and the bit error rate tester. The power supply is connected to the power cable here, and the bit error rate tester is connected to our victim cable. This is our cable bundle model, and it is connected to our DC to DC converter, which is connected to a 50 ohms load, and the victim cable is connected to a 12 ohms load. We are modulating the DC to DC converter from the controller, which is from the microprocessor, which is connected to a simulation here. I gave you a very brief description of the setup that we have here, but now we will get into the details. So this is the cable bundle model, which is the integral part of our setup. I'm using a white paper underneath the cables so that we can distinguish them. We have three cables, as you can see. The first cable is the power cable, which is connected to the DC power supply and the DC to DC converters. This is also the source cable, which is causing the interference. The other two cables are communication cables, one being the data and other being the ground, and these are the victim cables. These are connected to the bit error rate tester through a BNC connector, as we can see here. These cables, as you can see, are basically very thinly enameled and have no shielding, so they can cause interference with each other. The distance between these cables is just 1 centimeter, and their distance with the ground plane is 5 centimeter. This is very similar to the crosstalk model of PCB, where we use traces to show that the traces are having interference with each other in the form of crosstalk. But however, in a PCB model, we cannot change some parameters, some integral parameters that affect the crosstalk, such as the distance between the traces, which in this case we can change and observe how, for example, by changing the distance between the cables, the crosstalk is affected. So for example, in this case, I'm just using this random piece of block to change the distance between the cables, and as you can see, I can decrease or increase the distance between the cables, and by changing this distance, the crosstalk or the bit error between the cables is affected. Now coming towards the bit error rate tester, I told you about the power cable, how it is connected to the DC power supply, and the victim cables, the communication cables that are connected to the bit error rate tester through a BNC connector. The bit error rate tester basically transmits and receives a series of random bits and then compares them to calculate the bit error in this case. As you can see, the power supply is turned off, we have 0 voltage going in. So the bit error is also 0, but if I turn it on, we can see that now we have some sort of errors.
So in order to generate the signal that will be driving the converter to generate the interference, I am using this computer, which generates a signal. This signal is translated into the microcontroller, which I have here. The microcontroller then modulates the converter to generate, in this case, only one switching frequency. That switching frequency will be driving the converter. So the power flowing from the converter to the cable will be going from one end to the other end. As you can see here, I am using near field proof. The near field proof is used to measure what will be the interference of the modulating signal used in this case. As you can see here, if we move to the EMI receiver, we are getting the actual value measured from the near field proof in the EMI receiver. As you can see here, if I measure with a marker the maximum value of interference generated by this switching frequency, 50 kilohertz, I am measuring then a value of 60.551 dB microvolts. So previously we have measured a value of 60 dB microvolts. So after applying the modulation technique that it is the mitigation for the switching frequency, right now we can measure a value of interference much lower if we compare to the previous values of 60 dB microvolts. Now, if I move the marker here, I am measuring 36.53 dB microvolts, which at the end, this setup is not only used for analyzing crosstalk, but also to determine mitigation techniques that can be used in the industry.
Yes.
One,
So-
two, three. Start.
So to understand crosstalk in terms of magnetic coupling, there have been much research done in understanding PCB traces and crosstalk within them, but this is the first time we've attempted and have some conclusions about how crosstalk happens in a canvas system through a victim and source modeling and an experimental verification for that. What we believe or what we think through our literature review is that this sort of a problem hasn't been encountered yet in the industry, but that's what research is all about. We take problems which the industry will be encountering and we solve them before they encounter it, and that's how we add value to research at the University of Nottingham. Thank you.